In part 2 of Data in the Computer, we'll look at the remaining data types and how they're represented in binary. In the first part, we looked at numbers and saw that numbers are represented using the base 2 standard. Numbers in base 2 are not compressed, which means that there is no recording of patterns. Every bit that makes up the number is represented. Also in part 1, we were using this byte here and seeing what it represents with different types. For a number, we saw how that byte, using the base 2 standard, represents the number 67. For letters, things like you might type into a word processor or an email program, we saw that the standards are ASCII, the American standard, and Unicode. ASCII uses 1 byte per character, Unicode uses 2 bytes per character, where ASCII was the first byte. It's not compressed. We saw that under the ASCII standard, this byte would be the capital letter C. We also looked at graphics. We saw that this byte might be a single pixel of a color, like red. What the byte actually means is determined by the standard that the graphic file is saved in. If it's saved as a bitmap, which is an uncompressed format, it will have a color palette associated with a bitmap. GIF has a different color palette, and so does JPEG. GIF and JPEG are compressed formats, which means that not every byte is stored. Instead, patterns of bytes are stored. And in the first part, we saw a picture of a rose with potentially very large regions of white. Bitmap would have a byte for every pixel of white, where GIF and JPEG would simply store the fact that there is a repeated pattern of white. We will now go on and look at the 3 remaining data types that we started with. Sound, like you might hear on a speaker, video, played on a computer, and programs themselves, like a game or a word processing program. We will now look at how sound is represented in binary. Sound occurs naturally as an analog wave. When I speak, my vocal cords vibrate, causing a wave across the air, as we see here. The digital microphone that I'm speaking into right now picks up the wave and records it. So sound waves occur in analog. The computer must store things in digital format. The process of converting the analog waves as they occur naturally, such as my voice or music coming from a band, to the digital stored in the computer is called sampling. In sampling, the digital microphone records the sound level at every fraction of a second. So at this fraction of a second, it might record this sound level. At this fraction of a second, it records this sound level, and starts storing the bytes in RAM. As it goes along sampling, it's building up more and more bytes in RAM, representing the sound that's occurring naturally. Let's take a look at an example. A typical CD quality sampling with a digital microphone in a studio takes about 44,000 samples per second. Using 2 bytes to represent the amplitude of the naturally occurring sound wave, 2 bytes allows hundreds of thousands of different levels of sound. With 2 bytes per sound at 44,000 samples per second, the recording stores approximately 1.4 megabits per second as the sound occurs. For say a 3-minute song, that's 32 megabytes of information. This is a big download if you were to download a 3-minute song. The format that naturally occurring sound converted to digital is stored in is called wave. Wave is uncompressed. Similar to the way bitmap was uncompressed for graphics, wave is uncompressed for sound, which means that wave format stores a byte, or in this case 2 bytes, for every sample. So if we look at the byte that we used in part 1, that byte could be part of a sample or a sample of a sound, one little fraction of a sound. Like graphics, sound has compressed formats too to make it more manageable to work with. The most popular form of compressed sound is MP3. Like JPEG, MP3 does not store every sample, but instead it stores patterns of bytes that are found after the samples have been taken and put into wave. So again, MP3 is not storing every sample, it's storing patterns of samples. In addition to recording the patterns, MP3 also does something called perceptual noise shaping. Perceptual noise shaping utilizes the fact that MP3 is designed for human ears. There are other kinds of sound that may not be necessarily designed for human ears. MP3 is designed for humans to listen to. And there are certain ranges of sounds that humans can't hear. For instance, if several sounds occur simultaneously, the human ear hears the loudest one. There are sounds that are outside the range of hearing. MP3 is aware of this, and bytes that fall into noises or sounds that can't be heard by the human ear are eliminated when MP3 does its compression. MP3 usually achieves about 10 times smaller files. So the 32 megabyte song that we talked about before, the 3-minute song in 32 megabytes, using MP3 compression gets down to about 3 megabytes. 3 megabytes is a much more reasonable download. It was the advent of MP3 in the late 90s that made downloading music possible over the internet. It was possible before, but it wasn't widespread because the internet was slower and everything was stored in wave format, which meant very long downloads. With the internet getting faster and MP3 compression being used, it now became very reasonable to download songs, and we're all aware of the explosion in downloading that happened as a result of it. Let's move on and look at another data format, video. Videos that you see on a computer, or even animations that may not be video, just moving pictures on a screen, are single graphic images called frames sequenced over time. So here we see a picture of the large cat sequenced over time. In addition to sequencing the frames over time, an audio track can be synchronized with the frames to provide sound that goes along with the moving pictures. The most common and prevalent form of video is MPEG. MPEG format is just JPEG that we saw earlier. Remember, JPEG is a compressed format for images. MPEG is just JPEG images sequenced over time. The synchronized audio track uses the MP3 standard. So MPEG is sequenced JPEGs with MP3s. Now MPEG can do additional compression. In addition to the compression of finding ranges of the same color pixels that JPEG does, MPEG can find commonalities over frames and store those patterns. So if it's a night shot of panning the night sky and there isn't much but dark on there and it doesn't change for several frames, MPEG doesn't have to store every frame. It can store a description to redraw the frame several times. That again saves space in the file because not every pixel has to be stored. The pattern describing how the frames would look when they're played gets stored. Now DVD is a standard for laying out MPEGs on a disk. So if you watch a DVD video, the videos are actually stored in MPEG format on the disk. There are other animation formats. Real Player was more prevalent in the late 90s, early 2000s, .rm files, AVI files, which this video is in, flash files that you see on web pages with either video or animation, and animated GIFs. Animated GIFs are moving frames in a single GIF file. So the byte that we looked at before could, in addition to being text, sound, could also be a pixel in a frame of a video. Now let's look at our final form of data. The final form of data we listed were computer programs themselves, games, word processing programs, software that you install on your computer. Each program is made up of bytes. The bytes are treated as instructions, telling the computer's processor what to do. For instance, adding two numbers, move a byte from RAM out to a speaker, draw a pixel on the screen. Now, Intel processor chips, or chips based on what's called the Intel instruction set, have a certain standard that they use. In the standard, the byte that we've been looking at might be an add instruction. Now, there are other forms of processors out there. Macintosh, for most of its lifetime, was based on a different instruction set than most PC or personal computers that use Windows operating systems. Motorola chipsets, which was what Macintosh was primarily using, had a different instruction set where this same byte that might have been an add on an Intel instruction set might have been a move instruction on a Motorola-based instruction set. And this is why Windows-based software doesn't run on Macintosh and Macintosh-based software doesn't run on Windows. Now this is changing. As Macintosh starts to incorporate the capability to understand Intel instruction sets on its processors, Macintoshes are now becoming able to run Windows-based software as well. We have other lectures that talk about how computer programs are written and how they are translated into the binary that computers can use. But briefly, when a computer programmer writes a program, say a game, they write it in a language that usually takes ASCII input in something like Notepad or some simple text-based entry. They write instructions in a language that they learn. The instructions tell the computer how to perform. Then other software, usually called a compiler, reads the ASCII instructions in the language that humans can understand, languages like Java or C++. The compiler reads the ASCII and translates it to the ones and zeros, the adds, the moves, the instructions that the hardware understands. That's how computer programming is done, and the result of it is that the byte that we saw and have been using all along might be an add instruction that the compiler generated from some software that a computer programmer wrote to, say, play a game. So we've seen that that single byte that we started looking at could represent the number 67 if a number was being expected, and the 67 comes from the base 2 standard. It could represent a capital letter C, a colored dot in a graphic, a fraction of a sound, a colored dot or a pixel in a frame of a video, or an instruction like add. So how does the computer know what kind of data the byte is? If that byte could be any of those types of data, how does the computer know? The answer is, it depends on the context that the byte's used. If the byte is sent out to a printer, the printer will treat it as a pixel, and if it's a bitmap being sent out to the printer, it will draw the pixel in the appropriate place of the bitmap to start to fill in the picture. If the byte is sent to a speaker, the speaker will play that level of sound. If the byte is sent to a processor, it might add two numbers together. So that same byte can represent all these different kinds of data, and what it actually represents depends on how it's used. This chart summarizes the data types that we've talked about in Part 1 and Part 2. Numbers, base 2, aren't compressed. Letters using ASCII or Unicode, also not compressed. Graphics in bitmap, GIF, JPEG, where bitmap is uncompressed, GIF and JPEG are compressed. Sound in WAVE, which is the uncompressed format, and MP3, which is the typical compressed format. Video and animation use many different formats, MPEG being the most prevalent and the one used on DVDs, which is a compressed format. In fact, most of the video formats are compressed. And finally, we saw that programs could follow the Intel or the Motorola instruction set, and they're not compressed.